team always take a lot of time to do everything. Okay, finally. All right, so now that the recording's going, so today we will continue on from what we left off last week, right? Last week we were talking about how to design what is an ISA, right? And what is a microarchitecture and how to design a single cycle architecture, right? So ISA essentially define the list of commands that the hardware, the microarchitecture understand. When you build the chip, right, one of the key things here is the chip builder work with the people who, well, partly they're the same team, right? So they work with the people who had the ISA and then they'll implement every single functionality that the ISA dictate, plus the optimization to make every command faster. And the microprocessor, as we know it, is essentially ISA with the microarchitecture. That's the running chip that you got, right? The component of the ISA include things like instruction, the definition of how you manage the memory, the definition over how do you manage different system call, interrupts, asset control, priority and privilege mode, input-output thread management, and power thermal management, and more, right? The thing is, when I say and more, it basically means that as you extend the ISA, right, you can add more command. You can add more things that the hardware want to support. Sometimes, if you extend the ISA and it doesn't have the backward compatibility, then you have to figure out, okay, for the program that you compile with the old ISA, how do you make sure they still run, right? There was a problem back in the day in Intel when they kind of like worked with the Intel Itanium with their own version of 64-bit ISA, right? And toward the end, the AMD version of the 64-bit ISA for the x86 kind of wins out because it does provide a really good backward functionality, right? Even though maybe, who knows, right? Maybe the new ISA from Intel, there are some features that might be really good too. The problem is if you cannot really support old software and you have to like buy a new piece of software, that's a big issue with many business, right? So backward compatibility is important here. There's also things that we talked about last week where we talk about this terminology called architectural state. These are whatever the programmer sees. The important here is the programmer see exactly this. So let me ask you this question. When I write assembly code, you're going to expect the program to behave the same way as the code you have written, right? Line by line. That's what the architectural state gives you. So if you somehow say pause, right? In the middle of the computer running, if you can magically say, hey, stop. And then you somehow can magically peek into things you can peek from the programmer point of view, like register value or the memory, the content of the memory, then you can tell exactly where you are in the assembly file that you just launched, the program that you just launched, right? That's what the architectural state gives you. This is going to be really important going forward because from the programmer point of view, we just need to make sure we maintain this. Whatever we do in the inside, it can be any random state, right? Hopefully not random, but in any state, the architectural state is maintained so that the programmer knows that things are run in order. Then we also have states that are not visible to programmers. These are called microarchitectural states. And there's no way for the programmer to access this. Why do we have this? These are for performance. These are for things that we optimize in the hardware to make sure that whatever we try to do in the hardware, it makes the program faster. Or sometimes it makes the program more power efficient, right? And the basic is, think of it this way, the ISA is kind of like a method to command our computer. Add, subtract, right? The microarchitecture is actually the hardware inside and behind the ISA. So let's say you have the architecture state 1. right? And you want to process one instruction. What will happen is when you finish processing, you got to the next architecture state. And then we talk about data path versus control logic. And the difference here is essentially, right? Think of this as like a simple math function where when you have a functional units, you put in D1, you got D1 prime back. You modify the data. You get rid of the old version of the data and you replace the data with a new version of the data. And this is done through functional units. An instruction would determine what happened to the data. If you add something, the result, the new data should be the result of the adding two numbers together. Things have to make sense, basically, right? And processing instruction consists of two components, the data part, which is the hardware that govern how can I actually make the transformation happen. These are functional units like logic gates. These are the actual structure that move the data around. These are storage component like a register. And then there's a control logic to make sure you synchronize everything. You control the signal that control the data part. Control logic, think of it this way. Anything that control the data part are the control logic, right? And when we have this toy example where we have the PC and the decoder, when you go do the decode, right, things will get enabled and disabled accordingly, right? And we kind of wrap it up by let's do a single add, right? A simple add command. So when you go back to our example, let's say I have add, oops, 10, add 0, R1, and R2. And what I want to do here is, let's say I want to add 0 and R1 together and write the result into R2. So let's say this is what we want to do, right? The fetch part of this is basically, let's say this is line 20 in your assembly, right? And let's say this line 20 corresponds to the address, I don't know, 100, right? Then in this case, the program counter would be at 100. It simply is the address of that line inside the main memory. And please follow this a little bit and make sure you understand, because this is your lab one, right? So the address is going to read the content inside the memory at exactly at where the program counter is pointing, which indicates this case 100. You look in here, it's going to be this binary pattern, something that would correspond to this add R0, R1, and R2. That command, that binary, right, will be feed to the decoder. The most important thing in lab 0 and the most important of the decoder's task is to look at that bit pattern and figure out what is that command. In this case, it's add R0, R1, and R2. So it will first try to make sure R1 and R2, R0 and R1 get feed to the adder, so that the adder can add the two numbers and give R0 plus R1 out from the output port, right? Then you feed it back to the register file to store it back, right, as R2. And that's all. Then you increment the program counter so that it becomes 104, essentially the next line. And then you proceed until the program finished, right? So I did prepare slides for fetch, decode, fetch, operand, execute, store, result. We can cover everything in one slide. So let's do something else. Let's do a load. What is a load? A load is, instead of adding numbers together, you load the data from the main memory, right? So you do the same thing here. You try to get the instruction using the program counter, right? Then the instruction come in, right? Then you need to figure out, where do I load? It can be from the immediate, a part of your instruction. Or it can be something like, okay, I'm going to load whatever R1 is pointing, right? Then you feed R1 as an address or immediate as an address. that becomes the address for whatever you want to load. Then the data comes out here, and you might want to actually store that back to the register files. Then you select where you store, and then you again increment PC, go back here. So that's for a load, right?
Decoder actually decodes the address of the data in this case.
Decoder and the ALU would both work together to get the address. That's why I have the address come out of the ALU, because the load command has different format. Sometimes you can say load 0, 20. It means that I'm going to go to address 20, put that value to R0. So that will be immediate jump directly to the address. But if I have something like load R0, and then the address where R1 is pointing, then in this case, I'm going to go to get the value of R1. The value of R1 becomes my address, and then I load. Or I can do something like this, load R0, 10, R1. This is basically, I'm going to load the address at 10 plus R1. Because it has the plus, then I'm going to feed in 10 here and then R1 right here, and the result of the adder comes as the address for the load. So this depends, and both of them would work together to make sure we got the correct address, right? How about a branch? What is a branch? A branch is when you have things like if, else, or for loop. When you have this kind of transform your code in assembly. It becomes a jump instruction or a branch instruction. Both of them would basically change what? We change the line that we are running. You're not going to the next line anymore, right? So for the branch instruction, what is a major player here? PC. The major player is the PC because we don't know where we're jumping. So basically what you're trying to do is to select, are we jumping to the next line, PC plus 4? Are we jumping to some address that you just added together or multiply together? Are you jumping to some register value like R1? Or are you jumping to some constant address that comes directly from the instruction? Then the decoder will select the correct location to jump, and then you update the IR. So let's say earlier is line 100, and the next line is 104, right? But in this case, you want to jump to 200, then 100 will get updated to 200 to go to the correct line because you have a jump instruction. All right? Okay, so that's the overview of the different types of instruction and how it would behave in a super high level. Again, super high level, right? So today we'll then continue on to single cycle versus multi-cycle processor. Everything we did, yes?
How will it return back to the original instruction after the branch process?
There are two things that we have to sort it out, right? So first of all, right, for these two things, if you have the if else, do you have to return to the original?
Yes.
No.
No. Okay.
Because you have if else. You finish the if else, then you go proceed forward.
Yes.
Right?
Yes, yes.
For the for loop, the original is the jump target. Right? Because basically you go run like this, right? And if you do PC plus 4, let's say this is your loop, right? PC plus 4 becomes exit the loop. And if you have to jump, basically you jump back to the original location of your loop, right? So but that's a great question because that's one thing that would cause the jump, but you have to go back to the original. And what's that? Function call. Right? Because if I run my code and I have a function call here and I have a function defined here, right? Basically from this line, you have this function call, so you jump right here. Then you finish, you jump back right here. Right?
Yes.
So do you know what is a stack pointer and what is stack versus a heap?
Yes, I do know that there is some memory called stack where we push and pop the address, uh, and we,
So
uh,
you use a stack pointer to push this line. So
uh,
you basically push that line and say, hey, jump back here. And then you finish when you finish the function call in x86, for example, there'll be a command called literally called return. And what return would do is it would pop. So you have this line value back, written back to the program counter. So it basically would well, not internally, you have to write the code in assembly, but it would go to that stack pointer's value so that you know where you jump back. So that's how you handle function call, right? So that's why I said it's a great question, because this is basically how you make function call works. It's actually from the most of the work would be done in the compiler. When you compile the code, the assembly lines that correspond to this, I'm going to handle the function call, they are part of the assembly code, right? So this is what you should learn when you take a class that more of the like a basic computer system. They will talk about how assembly work, and then one of the major topic is how do you handle basically function call. So if you're curious, I did have a YouTube video for this topic. I'm gonna send it to you after the class. It's like part of the other playlist that kind of govern like basic computer system. So I'm gonna send you those lecture videos specifically for the handling function call, but there are 3 lectures that talks about assembly, right? So if you find those interesting, feel it might be a little bit slow because it's for the undergrad. So you can just fast forward or do things like that. But I think it might be helpful because it does have the animation on like, okay, when I have function call, this happen. When I have function call, these happen.
I do have one
Yes.
more question. Actually,
Yeah.
in the paper I read a term called branch prediction failure. In the paper named requirements, bottlenecks, and good fortune agent for microprocessor evaluation.
Yeah, we
So,
covered this in 2 lectures actually. So don't worry, we're actually gonna cover this in detail in 2 lectures.
all right.
Yeah. So basically, branch prediction. We're actually gonna talk about branch, like what happened when you cannot really go and have a branch instruction. So the failure would cause performance slowdown. Right? So you want to avoid this. But you talk about the cause and why is it not good, right? So
Right.
let's continue on to single cycle versus multi-cycle processor. So far in your lab 1, you're gonna implement a single cycle processor where everything, all the control signal is generated for that cycle. So you can transform D1 to D1 prime in the next cycle. The problem with that is that what dictates the clock speed is whatever instruction takes the most time, right? Because everything has to take 1 cycle. If you clock too fast, then if you have to run a slow instruction, you will not be able to do that. Because by the time you have the clock going, proceed, like say, hey, proceed, the guy who's haven't reached the finish line, he can proceed because he haven't reached the finish line. He can run the next lap, right? So you need to make sure the is tuned for the slowest instruction, which is bad because you don't want a 1 kilohertz processor. It's just not realistic, right? So the idea is let's decouple the clock, because let's say basically you're asking people to run in a stadium, right, in laps, and this is your finish line, right? And let's say I want to make sure everyone reach the finish line before I allow the next lap for you to run the next lap to proceed in a clock cycle. Then you might be asking question, why are you forcing the fast people to wait, right? I guess you can clock faster and let them go. And in the meantime, if people need multiple clock cycles to finish one lap, one instruction, just let them use more than one cycle, right? And that idea makes sense. This is called multi-cycle processor. So the main idea is, hey, let's decouple the clock with how long instruction take. You don't have to make sure everything finished in one cycle. If they don't finish, clock it. Let them continue, right? And that's the whole idea. You decouple. Basically, when we say decoupling, in this case, you separate apart two components. In this case, you separate apart the latency of your clock, the control signal, and the hardware itself, right? So you can clock it as fast as you want. And then if they don't finish, let them continue, right? Now, basically, that's our part of our topic today, multi-cycle architecture. So how do you process one instruction? When register gets the instruction from the memory, right? This is instruction register program counter would go to the main memory to fetch. But we typically call this a fetch. Then we decode the instruction. Then you typically get the operand, right? Most of the time for the context of this class, we will call this process decode. This is fetch, right? And then you execute, so we call this execute, right? And then you record the result and move to the next instruction. Typically write the result out, we call this write back, right? And because we have the memory component, sometimes there's a memory is part of the execute the instruction depending on whether you want to use the compute or you want to use the memory. But as you can see earlier, the load instruction can involve adding or multiplying. So typically, you would have to fetch, decode, execute, perform something in the memory or not, then write back. All right. So let's go back to our toy example, because one thing we discover is if you want to add R0 and R1 into R2, right? I first need to do this step. One thing I can do is I can clock them. Once you fetch, right? Once the instruction is here, I clock them. The next clock cycle, I'm going to use a different color, right? The next clock cycle is right here. Then I'm going to go through the decoder, figuring out, hey, what goes into the ALU? So that's the second cycle. Then again, I'm going to change the color. Now I clock them again. I just want to add, right? I'm going to clock them again. Then the last thing I can do is, well, I can do the next thing. I clock them, write the result back, update PC. And is that the same color? That's green, right? Okay. Sorry, I'm not really good with telling the difference between yellow and green. So in this case, I can clock it 4 times so that part of this process is done to part of the data path, right? So in this case, if we assume certain things, for example, if we assume memory take 1 cycle, decoding logic take 1 cycle, program counter take 1 cycle to write, register take 1 cycle to write, ALU take 1 cycle. Basically, everything take 1 cycle that involves like a state. Everything that involves a state or everything that involves adding, multiplying, take 1 cycle. Right? So how many cycles would it take to do an add? 1 cycle right here, right? 1 cycle right here, because you have to decode before you figure out what to do with an add. So 1 cycle right here, right? 1 more cycle right here. You don't have to do anything in the main memory, so write it back 1 more cycle. And at the same time, you can update the PC. So in the same clock, you can do both of them in parallel, right?
5 cycles.
In this case, actually 4. One here, one here, one here, one here, right? We skip the memory because there's nothing to do with the memory, right? So you can skip the memory.
Right.
Yeah, but when we talk about pipelining, these become 5 cycles. The key here is at the write back stage. At the write back stage, you need to update the register to make sure everything follows line by line by line in your assembly code. So in most, well, if not all, right, processor design, they are going to make sure this takes 5 cycles because if you have to do the memory, it should be there. So it's going to have this one memory stage where, in this case, do nothing, right? It would just proceed forward one cycle. It's just to have the in order write back. You write back in the same order as what you see in your assembly code. And because we assume memory takes the same amount of time, this is going to be 4 cycles as well, because the only thing you change is add and multiply, right? If you have to do a jump, right, then 1 cycle here, 1 cycle here, then you have to do this comparison, right? So 1 more cycle here, and then you update the PC 1 more cycle, again 4 cycle, because we don't do anything with the main memory, right? What if you have to load the value at the address that we provided? 1 cycle here, 1 cycle here. Because we don't do anything with the adder, you go directly to the address, 1 cycle, right, to load, and then 1 more cycle, right? So it seems at least simple, right? But think about it this way, right? In reality, memory would take a long time. That's reality, right? That's where a lot of the main bottleneck comes from. The main memory is the first wall behind making program fast. The second bigger wall is your I/O, when you have to go to the disk or storage or your network interface. That's even slower. And in your case, because you do a lot of video processing, right? Sometimes from multiple devices, you're gonna see the I/O as one of the main bottleneck all the time if you don't program it well, right? If you program it well, you will basically try to overlap those things, right? But the key technique is kind of similar. You try to overlap the slow process with something you can do in parallel. But in this case, right, most of the reality is adder, for example, would be faster than multiplier. Memory will take much longer, right? So in this case, if you have to add R0 and R1 together, the first step is where do you go? You go to the main memory. So that's by default. With our assumption that this takes 50 cycles, in reality, it's not even 50. It's actually longer than that. That's already 50 cycles, right? And then one cycle here, and then you update 1 more cycle. So that's things start to blow up, right? Now you can see as things start to blow up. In the real processor, the fetch process, it would not take 50 cycles because we do something to make this fast. But the key message here is if you don't do anything to how we design the hardware, your life is gonna be so bad, right? Because fetching is already taking so much time. Multiplying, for example, 50, and then instead of 1 here is 5 cycles. Make things even longer. 5 cycle on top is already close to 10%, right? 10% slower. That's not nothing. It's actually quite a lot of slow down, right? So does jump. Now things get slow. You have to go to the main memory. Fetch 50. Get your address another 50. Now you are at the more than 100 range, right? So this thing does take time. So how many cycles does it take? If you have the 1 cycle magic memory, as I said, if we have multi-cycle architecture, there would be 4, and then 4 more to do multiply, then 4 more, and then 4 more, right? Because we kind of establish that yes, this load doesn't involve any ALU, right? Just go to that address and load it. So everything takes 4 cycles. But this kind of seems slow, right? Because if you have to do it back to back to back, right? Add, then multiply, then XOR, then the load, right? Back to back to back to back. In the end, you're basically spending 16 cycles. And because you kind of add the fetch, decode, execute, memory, and write back, I'm sure you might have heard about this thing called pipelining. Over here, we are not doing pipelining yet. We are going to pipelining in a few minutes, right? But for now, multi-cycle architecture, we still run each instruction individually back to back. So it will take 16 cycles, right? So can we make this faster? Yes, we can through pipelining, right? This is now that we are gonna improve the utilization in your data path, because in the multi-cycle architecture, in a multi-cycle architecture, one thing that you might have realized is, let's say when you fetch the instruction, the decoder is not doing anything, right? Because you're running each instruction back to back. So when you fetch, nothing else is on. They're not really doing anything. When you decode, the fetch unit is idle, ALU is idle, nothing is actually on except the decoder. So the same thing happened to the ALU, right? So what if we keep pumping the next instruction? Let's say you finish the fetch. That instruction go into the decode phase. The fetch is empty. So what do we do? Hey, you have nothing to do. So let's process the next instruction, right? This is called pipelining. So I'm going to use this example that my teacher back at CMU, Professor James Ho, taught me when I was taking his class, right? This was back about 12 years ago. I'm going to have to do laundry. So let's say I'm a bum and I haven't do laundry in a long time. Let's say I have deadline, I'm lazy and I don't have time. Like no one loves doing laundry. Come on, right? That's always true, right? It is one of the extra work that you must do eventually. So what would happen in most cases? You try to group the laundry tasks together. You just not do laundry until you have like 5 batches of clothes, right? Then that day is lost, like because you have to do laundry. So you have 5 batches of clothes, and you have to, the process is what? Wash, dry, and fold them together, right? And you can't reorder this. You can't dry first and wash and then fold. Then you mess up the whole batch, right? You can't fold and wash and then dry. Otherwise, it will wrinkle, right? So you have to follow these steps. The reason why this is a good example is because you have to follow these steps. You can't reorder them. Wash, dry, fold, right? So your washing machine, you have, because you are a normal human being, you are not running a laundromat or something. You buy one washing machine and one dryer, right? There's no need for you to have multiple machines. Like why? And the washing machine usually is faster than the dryer. So let's say it takes 30 minutes and the dryer takes 1 hour, which is already too fast, but let's use that number. And you are a magician. You can move the clothes from the washing machine to the dryer in no time, right? And you still you cannot use your magic to fold the clothes, so that would take 30 minutes, right? So with that with this, what do? You would first watch the first batch, right? Dry the first batch and then fold the first batch. Without pipelining, what you have to do next is, once you're done with the first batch, this is multi-cycle architecture, wash the second batch, dry the second batch, and then fold the second batch, and so on and so forth. And this is not efficient, right? Because let me ask you this. When I finish washing the first batch, is the washing machine free? Yes, right? So I can use a washing machine to do what?
To wash second batch.
to wash the second batch, right? So this is exactly how. Wash the first batch, dry. So this is batch number 1, batch number 2, batch number 3, batch number 4, batch number 5, right? And then fold. Then you wash the second batch. When can I dry it?
When you fold the first batch, I think.
Yep. Right, and then you can fold. Wash. And then you can dry it right here. And now I'm fighting with PowerPoint. Just let's assume that's a wash. Yeah. Whenever I close to each other, they tend to delete that line. Okay. Wash, dry, and fold. Wash.
Do you have a touch pad, or are you using a touch laptop or some kind of touch?
Yeah, it's a Surface with the Surface Pen. Okay. And they tend to do this every time my pen get close to like the old line that I draw. All right. Let's try again. Yay. It works. So over here you see that, okay, let me ask you this. What's the bottleneck? So let's say I have more money and then somehow I'm rich enough to kind of like throw money at buying one more thing. Are you gonna get one more washing machine or drying machine or dryer? It would make more sense, right, for me to buy a dryer, because you see that, hey, that's your bottleneck, right? Again, the same thing goes with how you keep developing the pipeline, because you would then figure out, okay, what's slow? How can I make sure they are slow and balanced? So make sure that everything is balanced and fast, right? And this concept is called pipelining. This concept is applicable to many, many, many things in computer science, right? And computer engineering. In software development process, we also use pipelining. In an actual algorithm, we also can do pipelining. So this is a really, really handy concept. When you deal with I/O, you can also pipeline them. So in processor design, now we can pipeline things into 5, well, let's go with 5 stages for now. In a real processor, it's way more than this. If you own an iPhone or an Android phone, those processor is way more than 5 stages. iPhone, for example, is way more than 25. I'm not sure about Android because there's so many variants of the Android phone, but they have deep pipeline, really deep pipeline, in fact, right? To make sure they run really fast. But our textbook example would go with 5 stages because it is simple. It actually decouple each functionality really nicely. So you first fetch, then decode, then execute, then memory, and then do the write back, right? Now let me ask this question, right? Now that I have instruction in multiple stages, so let's say instruction 1 is in write back. Instruction 2 is in memory. Instruction 3 is in execute, right? Because I just feed instruction line by line by line. Right? These lines are electrical wire. These are electrical wires. So what's the property of electric wire? They share the charge. If electron is going through them, they will have the same voltage, right? So I have this line, as I said, data. How many instructions are sharing that line at the moment?
I think 1 can be at a time.
3. 1 in the execute, 1 in the memory, and 1 in the write back. 3 totally different instructions, which means that I need to support 3 different pieces of data, right? So now here's the problem. If I want to do pipelining, I need to make sure that is 3 different pieces of data. So what is a component we know so far that can store variable? Register.
Register.
Yeah, right. So one of the key issue in pipelining is, okay, we have to store in intermediate steps that are for that instruction. So everything that happened in execute should be for instruction number 3 right now. Anything that happened in memory, any component in the data path inside the memory stage has to be for instruction 2. Anything that is inside the decode stage, right, which is a lot, has to be for instruction 4. So you need to make sure you put in the register. We call this pipeline register. The pipeline register is trying to address a problem that, hey, wait, we have to store instruction intermediate values as well as the control signal for that instruction. Otherwise, your code is wrong, right? This is basically, we have to save the state. We have to save the state, right? We have to save the state. Otherwise, we lose the instruction. So the idea is, hey, let's add register to store this state because we have that. We can add them, right? These are called pipeline register. What's the downside of that? Register takes hardware component to implement, right? So it does comes with the additional cost because you need to store every intermediate value. This is basically the performance versus die area, right? So if you let's say I want to build chips for an air conditioner remote control. How much do I care about their performance? When I hit the button, does it have to be nanosecond fast, or if it's within half of the second, I'm okay, right? So for these things, do I need multi-cycle architecture? Probably not. I can make it as simple as possible and make sure the battery in here lasts like 5 years, which is not the case. Let's say it lasts 2 years, right? So that's the trade-off. Most cases in a real processor that you use for compute, most of them would have at least 5 to 7 pipeline stages. In the devices that you care about performance, like your phone, right? Then you go 20, 30 stages. Your server, your computer, they have a lot of stages, right? So these are the trade-offs. These are actually part of the beauty of hardware design. We need to know what's the demand. Do you want simplicity and cost, like low cost? I can just buy this processor like with a few dollars or a few cents, right? And that's it. I just need a simple integrated circuit. Or do I need something really, really complicated? Then you can vary this number of stages, right? So here's the pipeline register. I'm just going to replace that dashed line with this block. And I can't have a wider block because it would block something else, right? So I want to make sure it's clear that it separate out any signal here, right? It separate out signal that are crossing the boundary because you have to store them. One of the most clear example of things that you have to store are these output data, these address and data that are going into the main memory because it cross multiple stages. But one more thing, signal from the decoder, but I cannot draw it here, it's just too big. Signal from the decoder that say enable that adder, making sure you write to the register files when it's done. These has to be stored in the pipeline register, right? In the pipeline register. And now, let's say instruction 1 is here, instruction 2 is here, 3 is here, 4 is here, 5 is here, right? This is going to be the data for instruction 1. This will have to be the data for instruction 2, right? And these have to be the data for instruction 3. Is that clear? Basically, it's the same thing. Just make sure you store them specifically for that instruction, because if you miss that, your timing is off and then your code would have bugs. Well, in the hardware, right? It's not like the software has bugs, but in this case, your hardware is broken. And you don't want to sell broken chip. It won't sell because it won't even run, right? So now we talk about the pipeline and how we add the stages, right? Then the next question is we can add more stages. Let me go back one slide. Let's say if I can, yes.
Actually, I just want to ask that if we do not do pipelining, then the program counter will fetch the instruction in a sequential manner, first after second after the first, and in that case. But if we do pipelining, how will the program counter knows that yes, first instruction is in this stage and I have to run the second instruction now? Because
Great
there are
question. Great question,
multiple methods.
actually. Because of this. If you're not doing a branch instruction, if this instruction is not a branch or jump, what is the next value for a program counter by
Uh,
default? For sure.
+4, yes.
So if it's not a branch or jump instruction, let's say instruction 4 is in the decoder, you know for sure, right? PC +4 is going to be instruction 5. So that's easy. Now let's talk about branch. Now it comes to the paper you're reading, because with branch, it gets annoyingly complicated. Why? You're not picking this. Then you have to figure out, do we get this or this or this, right? How do we know? It has to be based on this instruction. By that point, there are two main things that we have to figure out, right? There are two main things that we have to figure out. First, is this a jump or branch? Because in the decoder, we don't even know, right? In the 5-stage pipeline, you know. In a deeper stage pipeline, sometimes you don't know because you are still in the first phase of the decoder. You haven't really know it's a branch, right? So you have to wait. So that's the first thing. How do you know it's a branch? Second thing, if you know it's a branch, where the heck are you jumping to? Because you don't know the target, right? So that's where branch prediction comes into play. If you predict correctly, nothing has to be done. Well, you predict and you jump to the correct location. But if you jump in the wrong line, what happened?
That will just change the algorithm or the
Yeah,
application that.
you are not running whatever the software wants you to run, right?
Yes,
So
yes.
you have to revert back and redo everything again to the correct location. So that's the issue with a branch and a jump, and that's a great question. I mean, that's a great question because right now with the 5-stage pipeline, you don't know where you're jumping until right back, right? If you have branch prediction, then you try to predict. If you don't do prediction, then you have to wait until the right back, which is not ideal, right? Which is not ideal. And let me ask you one more thing. Why is branch important? How many times you write code with if, else, or for loop? So let's say you stare at someone's code, right? What's the number of function call, if, else, and for loop? How many lines are those as opposed to any random like compute plus or minus? It's a lot. You write code in your code, it's likely to be 5 to 10% branch instruction, right? So with that, and let's assume the compiler doesn't optimize things, because in this day and age, there's also a lot of research going to, when you compile the code, can you group things together so you get rid of branches? So that's a pretty important area of work, right? But in the real code that people use, let's assume the compiler did not do any of that. You're gonna end up with a lot of branches, right? So adding more pipeline stages, you can have faster clock. The reason behind that is, let's say if I go back here, right, and I'm going to slice my adder into like 4 different stages, multiply into 10 different stages. Then I decrease the critical path, which means I can clock it faster, right? So that increased the clock cycle, right? And that's actually partially why when you have faster clock for the CPU, generally it means your CPU is faster. Because you pipeline, so that each clock cycle you are basically finishing one instruction, assuming that you can push everything through the pipeline, right? So the higher the clock is, the faster the rate at which you can finish one instruction. This would enable more structure to be active, right? At all time, you're gonna have higher utilization, which is good, right? What's the downside? Well, because more things are active, your power increase. It will consume more die areas because you need to add a pipeline register. And it's going to be complex to design because anything that you ask so far, wait, what about branch? What about the data in those wires? Then you have to make sure everything is correct, right? Otherwise, you have a chip that's useless, right? So you need to make sure things are correct. And again, what if there's a branch? So that's why I said that's a perfect question to ask. So how many cycles does it take with pipelining if I do this instruction again? Well, in this case, we have 5 stages, right? So the add take 5. But because we pipeline, we just add 1 to each of this, right? Because you basically pump through the pipeline with each instruction. So let me call this instruction 1, 2, 3, and 4. Wait, I think, yeah. So let's not assume this for simplicity. Everything in the ALU take 1 cycle, right? And in the next slide, I will have a table. I don't have a table. So let me draw this table that have instruction 1, instruction 2, instruction 3, and instruction 4, right? Then you fetch instruction 1, do nothing here. Afterward, you decode, right? You finish the fetching, so you fetch instruction 2. Still do nothing here because it's waiting for the fetch unit. Execute, decode, fetch, right? Do nothing. Memory, execute, decode, fetch. Write back, memory, execute, decode, and then you're done. Right, done. For instruction number 1, then you write back here, you're done. Instruction number 2, memory, execute, write back. You're done. Instruction number 3, memory, and write back. Then over here, you finish. Okay. Instruction number 4. How many? Whoops, sorry. How many is that? 1, 4, 5, right? 6, 7, 8. So in total, from 16 cycle, we just cut it in half with pipelining. And this would be even faster with more instruction because every time you add 1 more, it's going to be one more cycle. Assuming everything is perfect, right? Assuming everything is perfect, which is not real. For example, if you assume multiply take 5 cycles, these two would take longer time. It would occupy the execute for a long time, right? And that's when you have instruction stall. Instruction stall is because you don't have enough resource to move the instruction through the pipeline. Let me go back here. Instruction 1, right? Fetch, decode, execute for 5 cycles, right? So I can fetch instruction 2 right here. I can decode instruction 2 right here. Can I execute? If you are not pipelining the multiplier, you have to wait until the multiplier is free, right? So you can't do anything here. And you execute right here. I can fetch here because fetch unit is empty. Can I decode for instruction 3? I cannot because instruction 2 is still in the decode stage. So I cannot even execute. Over here, I cannot fetch because instruction 3 occupy the fetch stage, right? So this is called instruction stall because there's not enough resource to move the instruction through the pipeline. So what are the effects? The processor cannot fetch new instruction. It means the program is going to be slower, right? So what are the case? The earlier case is not enough functional units, right? Some of the steps take longer than the other, like memory or multiply versus add, right? Or I just unbalanced design. right? So what do you do? What do you do? Well, if you try to do something, these are the goal. Make sure it's still correct. As long as you make sure things are correct, you're fine. Okay. And to make sure things are correct, make sure that the pipeline register still hold the value for that instruction that you are there. And that's it. That's the key things here. When you fetch, let's say instruction 1 is right here, 2 is right here, and 3 is right here, occupying like this for 2 cycle, right? So cycle number 1, instruction 4 is here, 5 is here, right? Cycle number 2, what happened? Right back, it's done. Instruction 1 is done, right? Instruction 2, move here. Instruction 3 is like, oh, I'm still executing because I need to cycle, right? Do nothing here. Instruction 4 say, hey, I cannot move because instruction 3 is still in the execute. So I stay here, 5 stay here, right? Cycle number 3, what happened? So let me use a different color to make it a little bit more clear so I can have like this difference between cycle. Instruction 2 is done, right? You do nothing here, so you move nothing to the through the pipeline. You do nothing there as well, right? You do nothing here as well. Are 3 done? No, it needs 1 more cycle. So 3 stay the same. You add nothing here. 4 stay the same. 5 stay the same. So this is your second lap actually. Just make sure this happens. Then when 3 is done in the next cycle, I'm going to use a different color. Orange, I guess. 3 now move here. 4 move here. 5 move here. And now you can fetch the 6th instruction, right? Nothing is happening here because you basically have nothing. 3 is still in the memory. And then you proceed forward, right? So is it clear? Basically, when you have instruction stall, the key here is insert what we call a bubble. This is called a bubble. What is a bubble? It's a circular spherical thing that has nothing in it, right? So you basically insert nothing into the pipeline saying, hey, I'm not going to do anything because the earlier stage told me they haven't finished. And it blocked everything else. So you need to make sure things are correct, just insert the bubble. Sometimes we call bubble, sometimes we call no op. No op means no operation, do nothing. All right. And one more thing is, well, in case, let's say my program by default use a lot of multiplier. Can I add more multiplier to do things in parallel? Yes. This is called the super scalar architecture. We will go into more detail later when you talk about another technique called out of order scheduling. But super scalar architecture is essentially, can I add more of the resources that you need? If you know that you have to decode multiple things, add more decode unit. If you know that you need to add a lot of things, add more adders, add more multiplier. Then you need to figure out how do you process the instruction in parallel. We're not going to talk about it now. We'll talk about that later. Because, why? Why is parallelism good? Faster. Why are they complicated? Instruction has to finish line by line from the programmer point of view, right? So there'll be a lecture specifically for that. How do you ensure that from the programmer point of view, they see line by line by line by line by line? But when you run the program, you will see parallel thing happening. This is another thing that the processor that you buy nowadays do. Inside, without telling you, hey, this is what we do, to make sure program is much faster, right?
Professor, can we provide different clock cycles to different instructions? For example, we know that instruction stalls because one instruction is taking much more time than other instructions. So can we provide that instruction with a faster clock cycle?
Great question. Yes and no, right? Yes and no. Why is that the case? So let me. This is a little bit. It's a messy slide already, but let me put it this way. Most components here need clock as an input. So it means that there's another wire called clock that go everywhere,
Yes.
right? So when I said yes and no, is because if you want to use multiple clock cycle, you then need to make sure you have different signal for the clock, and you have to select which one are you using. That becomes a trade-off. There are some components which use a different clock cycle. Let me give you one example. Your DRAM. The clock cycle for DRAM is controlled by another controller, not for the CPU. So DRAM would operate at a much slower clock. I would say about 2 to 3 times slower, depending on the DRAM specification. These days, about 1.5 times slower. It's not that bad, but it's still slower than a CPU. Then, if you want to have multiple clock region, that's actually something that is possible, and some chip does this. You can actually have multiple clock region, so that's possible as well. It's used to not just to speed things up or slow things down, but to save power. Because when you have a slower CPU, you save energy. You save energy. So when you want to slow things down to save energy, that is a possible strategy for your processor. So that's a great question. You can have multiple clock cycle, right? We call this frequency domain.
Right.
So you can run things with different power, with different frequency. Oh, actually, no. Sorry about frequency domain. That was for signal and system. I think I said something wrong here. But you can theoretically feed different frequency from different clock. Or you can use the same clock, but add the component to change the clock frequency. So you can add circuitry to slow things up or slow things down or speed things up while maintaining the same clock signal going through your design, right? Then you just enable and disable certain components to make sure, oh, I want to speed things up, I'm gonna enable this part. I want to slow things down, I'm gonna disable this part, right? So these are kind of like the fun, the fun in when you design the hardware. So it's like the blend of both science and engineering, both the computer science and the computer engineering component. Computer science is like, okay, you have to make sure it's correct, functionally correct, provably correct, right? Then the science also has to cover, hey, physics. you can't violate physics law, right? Then the engineering part is like, how do we hack things together so we have what we want, right? So yeah, so go back to super scalar architecture, right? So we can add more and more components, right? So we can add more multiplier, for example, more fetch unit, more decoder, more adder, more interface to the main memory, right? And this is real. For example, have you built a PC on your own before? Or you've seen a picture of my motherboard?
Yes, I have actually purchased CPU in different components like separate RAM, separate CPU, and then
Oh,
I
great, great. So
uh,
if you look at a motherboard, sometimes they comes with the different color for your DRAM, right? There are two colors, for example.
yes.
Have you ever checked out what does the two color mean?
No, actually not.
So that when we go through the another lecture for DRAM, you learn what those mean. But I can tell you now that each color is controlled by a different controller. That allow you to have more bandwidth going into DRAM if you plug them into a different color.
Right.
The same color will be operated by the same controller. It's the same clock region. It's the same clock speed. A different color, because it's a different controller, then it's a different clock speed. Right? We'll go into more detail in DRAM lecture. But these are things that we do to make sure that you can even have more bandwidth, or if you somehow buy DRAM with different clock, you can actually access them with different speed, essentially. The goal of our design is, well, let's make sure things are balanced. Because when things are imbalanced, what it means is you buy some component, but it doesn't really become fully utilized because you don't use them a lot. That's when things are imbalanced. So your goal is to make sure things are balanced. So what are the cost of instruction style? The cost of instruction style. I think we're going really fast here. We almost I only have 10 more slides. So let's do a break here now that because we are transitioning into data forwarding. So let's do a quick break here. 15 minutes. We'll meet again at 10:30. Is that okay?
Oh, yes, yes.
And then we'll use the last, I would say 30 to 40 minutes if we finish early to kind of discuss like potential idea for the projects and things that any questions you have. All right.
Yes.
So let's do the 15 minutes break. We'll meet again at 10:30. When we are back, I'm gonna do another like maybe 5 to 10 minutes Q&A if you have any questions. If you don't have any question, we'll just proceed with the slides. Sorry that I go. Is that too fast, by the way? Because I
No,
feel like you have a pipelining background.
no, actually, I followed that lesson, today's lecture, and I am quite actually understanding that. I think
Okay.
this pace is okay with me. Yes.
Okay, cool. So let me know if I'm going too fast, because typically they will take this by the time I reach this slide is typically like 10:50. So we are about like half an hour earlier. So let's do a quick break. We'll be back again in 13 minutes. All right.
Oh, okay, all right.
All right. Okay, so let's continue on. So we talk about instruction stall, right? And that's one of the most important reason why when you run certain program, it gets slow while certain other program can be faster, right? Because when you run a program, sometimes that causes instruction stall. And let's kind of start to break down multiple courses of instruction stalls. And throughout the course, throughout this semester, we'll kind of learn how to address each of this. So the first one is instruction can stall because of the slide was freezing because of the long memory length as we showed earlier, right? We'll dive into this in the second half of the semester. Another course is branch misprediction. We will dive into this in a few lectures, but let me give you an example of what happened when we mispredict in the branch, right? So over here, when you have a branch instruction, so let's say branch is here in decode, right? So what most processors do is it would predict to be able to fill in what we should fetch next, right? We need to figure out what is the next PC. So in this case, it will start to do the prediction process. Let me call this a guess. It would instruction, and anything that I'm guessing would be in, let's say, in blue, right? Instruction and come in, which then would be fed to the pipeline. And because of that, then you're going to get instruction as a result, right? N plus 4, which is the next line, would come in, be fed into the pipeline. The one that you are not guessing, the one in this yellow, orange, I think, color here, branch. That's not orange. Here, I guess. It will be feed to the pipeline, and you don't know. You don't actually know when you are until you're in right back, right? That's where you commit, like, oh, okay, that's where I'm jumping. And if this is wrong, it means that there's gonna be multiple instruction inside my pipeline here, right? Which you have to get rid of. So to handle this, we are going to use some techniques that we're gonna talk about next. On top of branch prediction. Branch prediction, we'll talk about this in about 2 lectures. But first, let's talk about data hazard. Data hazard is what we call when there's this thing called data dependency. What does dependency mean? It means that to get my new data, I am dependent on earlier computation. For example, I have this equation, A equals B plus C, X equal Y plus A, right? Unless I finish this computation in the first phase, I cannot start the second computation because there's a dependency right there, right? And with this code, there's only one, there's a few dependency, right? First of all, if you want to add this into R2, it means that R2 is needed for the second multiply. Then R0 is needed for the XOR, right? So in this case, if we don't not even have to assume this, but you can see because I have this dependency, right? The multiply have to finish the write back for R2 to be updated, right? Because it has to finish the write back, which means that in the meantime, you have to stall because you cannot go into the execute because R2 is not updated, right? So if you look at it this way, right? Oh, sorry. let's say this instruction 1, 2, 3, and 4, right? So you're gonna fetch the first instruction, decode the first instruction, execute the first instruction, memory the first instruction, write back the first instruction. Then you fetch the second instruction. You are trying to decode the second instruction, but you cannot get R2 until write back is done, which is right here. That's when you can actually get R2. Once you have R2, then you can go into the execute stage, right? So the execute just basically has to happen right here because of data dependency, which is bad, right? Which is bad. So how can we make sure that R3 has the correct operand or the operand value? But before that, let's go into the type of data hazard, right? So you can have read after write or true dependency. And when we talk about the new technique called out of order processor, then you will have write after read and write after write, right? So in order pipeline, the one we have right now, we call this in order pipeline because we do everything in the order of what we see on your program. Then you only have read after write. So to deal with data hazard, as we said earlier, we put in the bubbles, right? We just, hey, I don't have the operand yet, so I'm gonna stall in the code and wait until everything is done, until I can go to the next step, right? So the solution is the pipeline register would send out empty instruction. This is what we call bubble or no op, right? But can we do better? We can do better with the technique called data forwarding. Data forwarding. So the idea is, let's say you have to do an add, right? Even though you're in the write back, you have the result of that add right away after the adder. Think about it. You have that result, right? It's a combinational logic. So once you go through the execute stage, the data out that come from the adder, that's what your data is, right? So the idea is, instead of waiting until the write back, you forward that result across the pipeline stages to the decoder stage. Say, hey, that's I'm cheating, but that's the result. I haven't commit, right? I haven't commit back to the register file, but here's the data. Go ahead, use it, it's safe. So this technique is called data forwarding. And this solve read after write. It solves read after write dependency because you want to read and your older instruction is trying to write and you have the data you're writing. So here you go, that's the data. Please proceed forward. Right? So the benefit is it eliminates stalling. In the pipeline, you tends to be able to eliminate most of the stalling. Right? So here's the quick overview of data forwarding. Right? So let's say you have instruction 5, instruction 4, instruction 3, instruction 2, and instruction 1 right here, right? And instruction 4 depend on instruction 2. Let's say it depends on instruction 2. It depends on the result of an add from instruction 2. So in this case, if you look at this data wire, right, there are 3 different versions of the data. The data for instruction 1, right, the data for instruction 2, and the data for instruction 3. And you know that instruction 4 need D2, right? Let's say this generate 0, this generate 3, and this generate R5. But let's say it generate different new value for each of these register. And let's say instruction 4 need R0, right? Need R0. And let's say instruction 4 also need R5. Also need R5, right? Both of them are in the pipeline. Both of them are being written back. So one thing you can do is take this and take this. Literally connect them, right? The way you connect them, so I'm gonna erase this line a little bit. So in reality, the way you connect them is you take this, put this in the mux, and put this in the mux so that the decoder can pick, hey, I know that whatever is in the register file is the old version of my data. I have to stall. So if I have to stall, I'm going to peek into the pipeline and say, hey, who produced that? Because I know I have to stall, it means that I know someone is producing that value. And then you will check instruction 3, 2, and 1. So who produced R0 and who produced R5? Get me that data. And you basically select the source that comes from the correct pipeline stages. So in this case, the select would be select one from execute and one from the memory stage, because one from the execute stage is generating R5 right now. And one from the memory stage is generating R0 right now. So if you pick those two as source 1 and source 2, you will get the most updated version of R0 and R5. And it's as simple as that, right? It's as simple as that for the 5-stage pipeline.
Professor?
That's
When we make some kind of microprocessor, then we just make the wires like if I design, I just make a single wire. Then this what you are talking about is the on the program execution decision. So how that it will take data? How will it decide that it will have to take data
Oh,
and
okay. So
data will
it will be a logic in here that I'm gonna make sure I select the correct input that forward that to the output. So do you know what is a mux? This thing?
yes, mux.
Yeah. So
Multiplex.
that's a mux. And the mux in here would take in the input from the register file, right? It will take input from the decoder from the instruction itself. It will also take an input from the forward path. So let me use a different color for the forward path. It will take input from the forward path across all the stages, right? And the select line in this case would select, instead of selecting from the register file, it would then select, hey, I detect data dependency and I know that R0 is in the memory stage. So in this case, I'm going to select the data forward from the memory stage. And when you want to gather R5, then again, you know that, hey, there are going to be this logic to check, right? Is there data dependency? And you then realize that, oh, okay, that's data dependency. So instead of getting data of R5 from the register file, then you're going to take that R5 from the execute stage. So the select line would actually have that. Are you from, like, have you used Verilog, VHDL, or any system Verilog, any hardware description language before?
Yes, we worked on Verilog in our FPGA course in our
Awesome.
undergrad.
So it's the same thing. When you write Verilog, in this case, you're gonna make sure you have a select line that select exactly from the data forward, this forwarded path. Yeah.
So actually, there will be multiple data lines coming to the.
Exactly.
Yes. Okay.
There'll be multiple data lines coming in from multiple sources. So if you build a chip, right? If you build, say, if you want to convert lab 0 into everything done in Verilog, right? Then you will actually replace the function call with just modules that takes in these wires as an input, and some of the red REG, right, the one that store the data as an input, and you store some of this. Some of them are wires that go through the mux, and you select the correct signal. Yeah.
Okay. Right. Yes.
So this is kind of like the high level of design. If you want to have to make sure it's more like a Verilog compatible design, then you have like then I need more I need more paper to draw. But it's essentially you're connecting these wires and select the right thing. Yeah. And if you want So if you somehow is curious and want to like try the Verilog side, or like let's say when you do that for your project, I have the starter code for this in Verilog as well. That you can try to do basically lab 1, but now in Verilog. It would actually, once you finish that, it would synthesize. And if you somehow have an FPGA that can do that, you can potentially put those things on the FPGA. But yeah, so this is how you can perform data forwarding.
Okay, yes, all right.
So that's actually the end of today's lecture. I actually plan to kind of cover like some data forwarding again for Opal because he missed today's class, right? In the recap for next week. And because we have a lot of time anyway, we should definitely have enough time to cover whatever we want to cover. Before we leave today, do you have any question about the assignment 1? Don't forget that once you assemble the binary, delete the first line that starts with the at. Otherwise, the simulator will not take this.
Actually, are you talking about lab 1 or assignment?
Lab 1. Yes, lab 1.
Lab 1, right?
This is lab 1.
Yes.
If you haven't started lab 1, do it now, please. It is not hard, but it does take time to actually understand the starter code and understand how everything works. And that time it kind of literally means that you're not going to code until you understand what you want to code, right? So that is a time that doesn't go into your grade at all until you understand what you have to put in. That's when I can give partial credit, right? So if you haven't started, please do it now. And you said you would review the paper, right?
Yes, yes.
Okay, so first of all, let me stop the recording so that I can post the lecture.
Yes.